some things can't be unseen. Look, probably there's a lot of people in the room who think of me as this kind of crazy guy who spends a lot of time looking at the internals of Unix file systems in a hex editor. Yeah. Well, this presentation is going to do nothing to correct that opinion. This is actually based on some ideas that I had when I've been, doing my Linux forensics casework. And sometimes you deal with investigations where, well, bad things happen to your file system, right? You're dealing with a damaged file system. And I wanted to talk about a couple of different cases. One is one that I actually experienced where our suspects became aware that, we were about to seize their systems. And so they did she's at the cops, let's remove the file system and try and get rid of all of the evidence. The other one can happen, just accidentally, right? You're going to zero that drive, for your next case. Oh, did I mean to type SDA? No, I didn't. I just overwrote at least part of my, primary hard drive. But you also see, people doing this for spoliation. Either overwriting the drive or putting a new version operating system on top of the nefarious stuff. So these are all cases where you've got either the remnants of a removed file system or fragments of a pre-existing file system, but things are messed up. And things are messed up in a particular way. In both of these scenarios, the situation you're dealing with is basically all the metadata is gone, right? So what ain't you got? You ain't got metadata. And, and that actually covers a lot of territory. So first off, all the inode information, right? So when I delete something in Unix file system, the inode associated with the file or directory that I deleted is mostly zeroed out. So all of the block pointer information or all of the extent information gets zeroed out. You lose that mapping to where the content of the file used to live on disk, right? If somebody overwrites the file system, the inodes in the beginning of each block group get overwritten. So you lose all of that inode metadata. You don't know where the files used to live on the disk anymore. ext, at least from ext3 forward, it's a journaling file system. So you think, oh, okay, well, I'm going to go look at the journal. Well, the problem is, if I just rm-rf the entire file system, so many journal transactions happen during that event that you basically overrun the journal. You overwrite the old stuff. So the journal doesn't give you a very large window of what happened to that file system. So you can't really use the journal to reconstruct things. If the file system is damaged, you may have even lost the inode for the journal. So you don't even know where the journal lives on disk. So you have to go groveling around through unallocated to try and find and reconstruct the journal blocks, which are spread all over the place. And the other thing is, and it turns out that in my research, the last one was actually the most difficult one for me. The block and inode allocation maps that sit up at the beginning of the block group also get overwritten. So you're going through, trying to recover blocks from the remaining disk space, but you don't know which ones of those blocks are actually allocated in part of the file system or which represent old data. And that, as it turns out to be a hassle. So all of this metadata is completely gone, but I still wanted to say, okay, so what can I do as far as file system recovery, even in a scenario where I basically have no metadata that I can work with? So what do you have left, right? So what you have left is at least some of the actual data blocks that used to be in the file system. And in those data blocks, you've got directory content, right? So Unix file systems, basically, directories are nothing more than sequential lists of entries. And those entries, all they do is they map file names and directory names to inode numbers, right? So here's an example, right? This is partial directory. So let's say this is my home directory. If you look at the internals of that directory file for home HAL, what you see is the sequential list of entries. And they're not even in alphabetical order. They're basically in the order in which the objects were created in the directory, right? So every directory starts with the dot and dot dot links that, the dot link points to the directory itself, the dot dot link points to the parent, but then you've just got, a bunch of entries. So inode number 127153 is a directory, the file type is also stored in the directory file, called downloads, and then there's my desktop directory and my .profile file and so on. Just bang, 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 one after the other in this directory file. Okay, now, if the file system is whole and fully connected, okay, that's my home HAL directory. But if I'm just groveling around in a damaged file system and I find this block of directory entries, I don't actually know the name of that directory. I know there's a block that has, downloads, desktop, .profile, and .ssh directories. So it's probably some user's home directory, but I don't particularly know which user it is, right? Okay, so that's part of the problem. You're running around through this damaged file system and you keep finding these directories, but how do you reconnect them back into the original contiguous file system? Well, look, okay, so this is, this was, at least at one point, the home HAL directory. So somewhere else on the disk, I'm going to find a block of data which was the /home directory, right? So if I look at that block of data, there's an entry in there for HAL, right? There used to be a home HAL directory. So this is where, the intelligence starts coming in. All right, so think about it, right? So home HAL has a dot link that points to itself. And that dot link tells us that the original inode associated with this directory was 127151, right? I don't know the name of the directory, but I know what inode used to be associated with it. But if I look at its parent, the old home directory now, there should be an entry, right? So there's an entry that corresponds to that 121 or 127151, right? That actually tells me the name associated with that inode, right? So if I can find the parent, I can match up the inode numbers and go, oh, cool, 127151 is HAL. Right? So that's how you can get to a file name, by tying the inodes together. So you have to find the parent and then use the dot linkage to figure that out. But you also have the dot link. So, by way of confirmation, right? I know that in the original home HAL directory, there's a dot link that points back to its parent. So it's inode number 18350, right? So the dot link in the parent should be the same inode number, right? So 18350 should be the inode associated with the dot link in the corresponding parent directory. So you can use that for confirmation, right? As you're going through and you're finding all of these directory blocks floating around in the file system, you can use these linkages to tie everything back together. And ultimately, if you find enough of this, you can begin reconstructing the original file system even without any of the metadata. I mean, we're just like brute force, raw parsing the directory files. But it kind of works. So, great, but how do I even locate these directory files? I mean, in a connected file system, it's easy because the inodes are there and you can find the directory file content. But with the metadata gone, how do I even begin identifying these directory blocks in order to begin parsing them? Well, the answer is, if you think about it, there's actually a signature associated with directory files, right? So we can actually use the signature to carve for the directory blocks. And to understand that signature, you have to look a little bit more closely at exactly how these Unix directory entries are structured. Okay, so the first thing that you need to understand is that Unix directory files must begin with a dot and dot link. So they always have those two entries right at the front of the block, okay? So you're thinking, well, if I could characterize what those entries look like, I should be able to create a signature, and that's exactly right. So a directory entry is actually, it's a variable length record. The first 4 bytes are always the inode number, whatever inode number that happens to be. And then the next 2 bytes are the total length of the directory entry. including the inode field and the entry length field, right? It's worth noting that directory entries in Unix file systems are 4-byte aligned. So, in the case of the dot link, I could actually fit that directory entry into 9 bytes. But because everything has to be 4-byte aligned, the dot link is always 12 bytes long, so it's rounded up to the next 4-byte quantity. Okay, so you've got the entry length, and then the actual length of the file name, which in the case of the dot link is just 1 character, right? So that's, 1 byte long. Then you have a byte, which is the file type, okay, the file type code. 2 is the code for subdirectories. And then you actually have the file name. Now, in the case of the dot link, there's 3 extra bytes in the directory entry, so we round up to a 4-byte quantity, and those are just null filled. Okay? So once you put all that together, I mean, you can see it on the slide, there's actually a very nice signature for that initial dot entry. There's going to be 4 bytes of whatever the inode is, but after that 4-byte offset, it's always going to be, a 12-byte directory entry length. So it's little endian, so 0C00. And then the length of the file name is always going to be 1, and then the type is always going to be 2 because it's always a directory, and then the file name itself field is always going to be 2E and then nulls. Right? So that's a nice, 8-byte signature, offset 4 bytes from the beginning of the block. And it's very easy to pull out the initial directory block using that signature. So that's what you do. You basically just run through the blocks looking for that signature. And you can, begin finding these and parsing them. Okay, so great. So we have this idea that if we find these directory blocks and parse through them, we can, maybe reconstruct the file system by using these inode linkages. Okay. Nothing is ever that easy, though, right? So typically, Unix directories tend to be small. 90 or more % of the directories in your Unix file system are only going to be a single block long. And so that's great. I mean, we can locate the blocks using the signature we saw on the previous slide, and we're good to go. But 5 to 10% of the directories in your Unix file system are going to be large enough that they need to go across multiple blocks. Unfortunately, typically, directory files that are more than a single block tend to be fragmented. And the reason for that is the way Unix file systems tend to do block allocation. So the way this works in Unix file systems is blocks are grouped together into these block groups that are scattered throughout the disk. When you create a new subdirectory, it goes into the least used block group, basically. And then as you add files in that subdirectory, the file system driver tends to allocate the files in the same block group with its directory. So the problem is, you start off with a small directory and you keep adding files and keep adding files, and the directory grows to a point where the directory file needs to glom a second block onto it. By the time that happens, all of the blocks near the original directory block have been allocated to files, and so you almost always will fragment the second block of the directory file. So the problem for us reconstructing the file system is, okay, I can find the initial block of the directory by using the .link signature, but what happens if it's a big directory? I don't know where the rest of that directory file is. So that was an issue. The other thing that you have in active file systems is, things get deleted. And so there's some interesting detail around parsing deleted directory entries, which we'll talk about in a little bit. There's also this problem where there's just churn, right? So, a file or directory is created in a temp directory, for example, and then it gets deleted, and then its inode gets reallocated to some other file, right? But there may be copies of the old data floating around, right? And as I discovered when I started doing this in real file systems, there's actually like a lot of copies of the same directory data because you end up finding copies of the directory block in journal entries, and it's just it's nuts. There's actually quite a lot of conflicting and redundant information that you have to somehow navigate through to try and build an idea of what the original file system was. So I want to talk a little bit about some of the points on this slide and describe a bit of the pain that I went through when I was trying to deal with this. All right, so let's first talk about deleted directory entries and how those work in Unix file systems. Okay, so we start with a simple directory. It's got 5 files in it plus the dot and dot lengths. By the way, quiz time, there's an RMO in it for the first person who can tell me what the file names are in this directory. Okay, so while you're working on that, so here we've got a simple directory, right? So we've got 5 files, bang, 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 plus the dot and dot length. One thing to notice here, check out the entry length field, which is the second column, on that last entry. You see it's a big number. Remember, it's little endian, so it's 0FB4. Okay, so you know, for those of you who don't want to pull out your trusty calculator, I'll do the math for you. That number corresponds to 4020. If you do the math on this, there's 76 bytes of directory entries preceding that entry, okay? And so the way this works in ext file systems, the last entry is always block aligned. So, you know, however much space is left in the block, that's what the length of the last entry is, okay? Directory entries are not allowed to cross block boundaries. So anyway, so just a little note there. Okay, now, let's see what happens to this directory if I basically rm minus rf that directory. Now, if I rm minus rf that directory, the inode that used to point to this directory is, you know, zeroed out, but the block that was that directory file is still there on disk, and you can take a look at it. And what you see, you know, just at the surface, take a look at the entry length for the dot field. You'll notice that it's another big number. So what happens when I rm minus rf a directory is all of the files get unlinked from that directory. So just before the directory itself is unlinked, it's an empty directory, okay? And so that's what you see there. The entry length for that dot length is actually, you know, 4084. It's basically the 12 bytes of the dot entry and then everything else in the block, right? Okay, but if you look past that dot entry, you can still see the original directory entries for the files that used to be in that directory. They're basically now in the slack space of the directory, the unallocated space of that directory. But you can go parse them out. They haven't moved. The data's still there. The inode numbers and the file names are still there. So you can parse them out. And this is the way deletion works in Unix directory files. When you delete a file somewhere in the directory, the previous entry grows to basically consume the old deleted directory entry, right? But the old directory entry is still there and can be parsed out if you go looking for it. So one of the things that you need to do when you're groveling through these Unix directory files is if you've got a bunch of slack space at the end of a directory entry, go look at that and see if it's a parsable directory entry. You know it has to be 4-byte aligned, right? So you can write some parsing code to go find the deleted directory entries. Because, you know, in this case, the deleted directory entries are interesting. They tell me the file names that were in that directory originally. Anybody got the file names yet? On. Correct. Good call. Good catch. Okay, so, all right, so great. So now we've got, you know, deleted directory entries that we care about, and we need to parse for those. Now, the other thing is this, you know, thing I talked about with inode churn, right? You're going to find a lot of conflicting information when you go through a Unix file system. You're going to find a bunch of blocks that all talk about the same inode number. And they may tell you that that inode number is associated with different file names, okay? So you go parsing through the blocks in your file system, your damaged file system, and you find 12 blocks that say, you know, inode number 390936 is temp systemd, some random GUID that has NJU in it, okay? And then you find another 10 blocks that say that same inode number, 390936, is temp systemd, some other GUID that starts, you know, QYK something, right? So the question is, which information is correct? Which do you believe? If you're trying to reconstruct the file system, which one is it, right? Okay, so since I can't really see people, we'll do this by applause. How many people think it's the first one, the 12 blocks that say it's, you know, systemd, NJU, blah, blah, blah. So applaud if you think that's the one. Wow, okay. Okay, that guy. All right, so how many of you think it's the second one? It's the 10 blocks that say QYK. Wow, nobody is willing to put their money where their mouth is on this one. Okay, so there was more people that said it was the second one. Guess what? It's neither one. The file had actually been completely unallocated from the original file system. What you're finding is old residual data that actually isn't even relevant to the original file system. Welcome to my world. Okay, so this gives you an idea of some of the complications that arise, you know, trying to reconstruct this information into a meaningful file system. So I spent a bunch of time beating my head around this and trying to come up with little heuristic methods and things like that. And I've got a tool now that I think is about, you know, 95, 98% effective at rebuilding the original file system just from the basic data blocks. And I checked that in to a new GitHub repo this morning before I came down. And with apologies to David Kovar, I called the tool AnalyzeEXT. Some of you may have used David's Analyze MFT tool, and I'm sure I'll get a complaining email from him from stealing his idea. So anyway, so there's an AnalyzeEXT tool that you can use that will try and reconstruct a file system layout purely based on data block information that it finds in your image. It also can just dump out raw information about what it finds in these directory blocks, and it dumps it out in a tab delimited format so that you can like load it into a spreadsheet and process the data that way.